Let's continue ZEUS training. Section 12, Stability Derivative Module for generating aerodynamic stability and damping derivatives. So the functionality of this module is to compute the aerodynamic stability derivatives that are generated from the frequency domain generalized aerodynamic forces at 6 internally created rigid body modes at a small reduced frequency. These frequency domain generalized aerodynamic forces are computed using the linearized Euler solver or the K-expansion method. And a typical output of these stability derivatives is as shown here. So this is a copy of the output file from ZEUS. So we can see that ZEUS prints out the reference area, chord, and span, and the moment center, which it uses to compute the coefficients. Then we print out the Mach number, and then finally we have the coefficients printed out here. So for example, CL alpha here per radian is, wow, 3,635.1. These must be unrealistic values. Here, what do we have? Reference chord is 1, or sorry, reference area. Okay, yeah, the reference area is 1. And the reference chord is 22. So that's why this CL is so large. So this is the stability derivative bulk data card that is referred to from the case control section. So we have an ID number, then we have the Mach number, then we have an ID ST flow. This is an identification number of the ext file bulk data card, which specifies the file name containing the steady flow solution. So let's explain this in remark 2. The steady flow solution must be saved by the ST flow bulk data card prior to the stability derivative analysis. Therefore, the file specified in the ext file bulk data card must exist. So what you must do here, this is kind of a complicated card to use. First, you must run another analysis, for example, Flutter or GenGAF, and then that card refers to the ST flow. And then in the ST flow card, you can put the entry save stop. So what save stop will do is save the steady flow and then stop the subcase analysis as soon as the steady flow is saved. So for example, if you use a Flutter subcase to compute the steady flow, the ZEUS will not go on to compute the actual Flutter analysis. As soon as it computes the steady flow, it will stop. And then you can move on to the second subcase, which would be the stability derivative, and then this would acquire that steady flow. Next we have gamma, which is the specific heat ratio. The default is of course 1.4. Next we have an epsilon parameter, EPSC. This is the convergence control for the linearized Euler run. This functions the same as the epsilon parameter in the MK per al card. So the default is 4 orders of magnitude here. So what happens here is if during the linearized Euler solution, the residual drops by 4 orders of magnitude, then the computation for that particular mode will terminate even if you have not gone the prescribed number of steps. Next we have a print field. This is the CFD convergence history print flag, where the default once again is 2. So 2 is print out the full convergence history. Print equals 0 suppresses the printout of the convergence history, and then print equals 1 only prints out the last Euler cycle of the last subiteration for each time step, or pseudo time step I should say. Next we have the CFL number. Then we have n step, which is the number of time steps to compute the linearized Euler solution. And then we have Newton, which is the number of Newton subiterations. N cycle is the number of Euler cycles per Newton subiteration. And then we have the LVR SMOO, which is the residual smoothing flag. So the default is on, but you can change it to off by specifying 0. Then we have TVD COEF, which is a parameter involved in the TVD form of the pressure sensor of the JST scheme. The default is 0, but you can increase that to reduce the undesired zigzag pressure distribution. And then finally we have the VIS2 and VIS4, which are the second and fourth order artificial dissipation parameters for the Euler solver. So note here that this card does not refer out to an MK param card or an MK Aero Z card. We just directly specify the Mach number and Euler solver parameters. And then we've already talked about all of these remarks. So here's an example. We have the aerodynamic stability and damping derivatives of the L56A18 wing body tail configuration. So this aircraft can be fitted into one block of mesh as shown here. And then our case control section. As I said, we have to set up a fake flutter run. So this flutter subcase only performs the steady aerodynamic analysis, and then subcase 2 will actually compute the stability derivatives. So in our flutter subcase, that's going to refer out to the ST flow card, which will save the steady flow onto a file, and then the second subcase will refer to that steady flow to then compute the aerodynamic stability and damping derivatives. So here's the first subcase, which is the steady flow. So we have 151 pseudo time steps, 4 Newton subiterations and 2 Euler cycles, and then the convergence history is printed out as shown here. And then our the steady flow parameters are shown here. And then note here that the steady flow solution has been saved on the file flowsol.dat, and then the analysis is terminated after the steady computation due to save equals save stop in the bulk data card ST flow. So because we have save stop in the ST flow card, the flutter analysis subcase terminates after the steady flow computation, so we don't go on to compute the full flutter analysis. So then moving on to the second subcase, the stability derivative card refers to the ext file card, which refers to that flowsol.dat. And then the stability derivative module employs the linearized Euler solver to solve for the unsteady aerodynamic forces at the 6 rigid body modes at a small reduced frequency. Therefore, the linearized Euler solver is executed 6 times for those 6 rigid body modes, and the iteration history of the linearized Euler solver is shown here. So we've cropped or pulled out a section of the output file, and here we have the convergence history of 2 of our modes. So this is mode 1, and then this one here is mode 6. And note that mode 1, it only ran for 170 time steps. And our second one only ran for 79 time steps, and that's because we achieved the 4 orders reduction in residual, so in only 79 steps. So after 79 steps, the computation terminates and carries on. So then the output file will output the stability derivatives as shown here. So here we've got some realistic values for our reference area, reference chord, and reference span, and we have our moment center. Mach 0.6. So now if we look at CL alpha per radian, we've got 3.3. If we want to look at CL alpha dot, that's down here. So we've got 2.1. So the first column lists, let's see, this should be the first row. Actually, the first row is alpha. First column is the drag. So this is everything due to drag. So CD alpha, CD beta, CD P rate, Q rate, and so on. The labels listed in the first row, which are up here, CD, CY, CL, CR, CM, CN. That's CD is the drag coefficient, CY is the side force, of course CL is the lift coefficient, CR is the rolling moment coefficient, CM is the pitch moment coefficient, and CN is the yawing moment coefficient.